Hey guys, Andre from High Performance Academy. Welcome along to another one of our webinars. This time we're going to be talking about a topic that kind of crosses over between both wiring as well as engine tuning. We're going to be talking about the topic of pull-up resistors. And this isn't a particularly complex topic, but if you don't understand what a pull-up resistor is, how it works, and how to properly work with a pull-up resistor in your chosen ECU, then you can set yourself up with a few potential problems, particularly with the likes of digital inputs. And if you are going to be adding in a two-wire analog temperature sensor into your ECU, you're also going to need to know about these. As usual with all of our webinars, if you've got any questions while I am presenting here, please feel free to ask those in the chat and the team will transfer those through to me and we'll deal with those questions at the end. So I think we probably should start off with what is a pull-up resistor and why do we need one? So in general, there are two areas that we will use a pull-up resistor. One is where we have a digital input. So let's say, for example, a driver controlled switch inputting to a digital input pin on our ECU. In this case, we'll talk about this in a little bit more detail shortly. In this case, the pull-up resistor is necessary so that the ECU can distinguish between the switch position, whether the switch is switched to ground or whether it's in the open position. Without the pull-up resistor, when the switch is in the open position, the voltage that the ECU will see is going to be undetermined. It's going to be floating. So it means that without the pull-up resistor, the ECU can't tell if the switch is open or closed. Now I've just talked about a switch, but there are also digital input sensors used for the likes of engine position and engine speed, which are exactly the same situation. They switch between a low voltage and a high voltage, and some of these will also need the pull-up resistor. Likewise, if you are dealing with an analog temperature sensor, so I've got a couple of these here. We'll just have a look at these under our overhead camera. So this is a fairly standard Bosch air temp sensor. It uses the 2-pin EV1 style injector plug, and then we've got a slightly more modern 1/8 MPT fluid temperature sensor. The thing you can see, particularly with this one here, is that it has two wires on it, and this is important with a temperature sensor like this. They're referred to as a negative temperature coefficient thermistor, and they don't output a voltage which our ECU needs to see in order to decide what the temperature is. Instead, what happens with the NTC sensor is that the temperature will result in the excuse me, I'll just get this up on the screen so I can show. The temperature change will result in the resistance of the sensor changing. So it's the resistance that actually changes, not the voltage, but the ECU doesn't detect that resistance. So we need a way of converting that change in resistance into something that the ECU can understand as a variable voltage. So, all right, while I was messing around there, let's just jump across to my laptop screen for a second and we'll have a quick look. This is the data sheet from Motorsport Electronics, who produced that little 1/8 MPT sensor that I just showed you, and there's a couple of bits of information that are important on this sheet here, but for a start what I wanted to just show you is that this graph here represents the change in resistance with the change in temperature. So you see quite a large non-linear variation in our resistance as the temperature changes, and of course there is a little data sheet over here that shows you exactly what that resistance will be at each particular breakpoint for temperature. All right, so how do these work and why do we need them? So first of all, what I think we'll need to do is head across to have a look at a diagram here of how the circuit looks for a digital switch. So this is a driver controlled switch, which I've already talked about. So here on the right hand side, we've got our ECU. We've got our switch, which is represented here by this broken circuit, and one side of the switch is connected straight to a 0 volt. So generally this will be connected to a sensor 0 volt circuit on our ECU, and then we've got the other side of the switch, which we can see here, is connected to the digital input pin on our ECU header. Now, the problem is here that if we forget for a moment about this little circuit here, which is our pull-up resistor, without that pull-up resistor, when the switch is open or closed, the ECU can't distinguish between that difference. When the switch is closed, it's going to switch to 0 volts, but we need a change in voltage when the switch is open so that the ECU can detect or sense that. So this is where our pull-up resistor comes in. Now, this is being drawn externally. So pretty obvious there, it's outside of the ECU. The reality is that most aftermarket ECUs on the digital inputs will have a software selectable internal pull-up. So we don't actually have to do any wiring here, and this will all be controlled electronically. It's all held inside of the ECU, but still the circuit is still going to show us what happens here. So one side of the pull-up resistor here, where it goes into the ECU header plug, this will be connected to plus 5 volts. I'll try and draw this without making a mess of it. There we go. It actually looks pretty tidy, happy with that. So we've got plus 5 volts going on there. And in this case, if we've got plus 5 volts on one side of the resistor, and we've got our switch open here, what of course is going to happen is that when the switch is open, 5 volts will also be present at our digital input pin. So in the open position, the ECU is going to see the input on that circuit at 5 volts. Of course, when we close the switch here, this completes the circuit will go to ground, and we'll end up with our voltage at that pin on the ECU at 0 volts. So this is what it causes. The pull-up resistor creates a difference in the voltage that the ECU will detect when the switch is in the open or closed position. Now, the pull-up resistor, while there isn't a fixed resistance that must be used, generally the resistance is the resistor that is favoured is the 1 kilo ohm or 1000 ohm resistor. So what this also results in is a really small amount of current in that particular circuit. So that's why when we switch to ground, we're going to end up with that voltage dropping straight to 0 volts. So we're going to have a look in an ECU just to get an example of what that actually looks like in the tuning software in a moment. But as I mentioned, that's one use of the pull-up resistor. The other use of the pull-up resistor is where we are going to be using a negative temperature coefficient thermistor, our 2-wire thermistor that we've already looked at. So what we'll do is have a look at that particular circuit. So pretty much exactly the same. In this case, what we've done is we've taken our switch out of the circuit and we've added in our little Bosch air temp sensor there. So what this does is it creates what's called a voltage divider circuit. So we've essentially got a resistor here and we've got a resistor here, and this controls the amount of current flow between the 5 volt pin at the ECU and the it's going obviously to ground at the other side. So what we end up now with is a variable amount of voltage depending on the resistance of the thermistor. So what I'm actually going to do, I think I can probably draw this slightly better. That's going to give you a slightly better idea of how that will look. So just bear with me for a second while I do this. So what we'll have is our resistor here, and this will be our 1 kilo ohm pull-up resistor. Then we come down to our thermistor, which I'll just draw in here. In the middle here, we've got our voltage out to our ECU, and then we're going to have this connected to ground. So again, I'll just try and quickly draw this in. So we've got 5 volts here. We've got our 1K pull-up resistor here. And this is our, let's say it's an IAT sensor. Horrible drawing, I'm sorry. And then finally we've got our output here to our ECU. So how this works, it really comes down to the real basics of electronics, which is Ohm's law. So this is with Ohm's law, we need to know our voltage and our resistance, and we can work out the current flow in that circuit. And then once we know the current flow, we can work out what the voltage is going to be at the ECU. So V equals I times R. So if we've got 5 volts there and we've got our 1 kilo ohm resistor, our our 1 kilo ohm pull-up resistor, and then we've got our intake air temp sensor. We add those two resistances together. Obviously, the air temp sensor resistance is constantly changing, but if we add those together, we're going to be able to find out what the current flow through that entire circuit is. So we're going to be able to get our current flow from our 5 volt sensor supply voltage down to ground. Once we know what our current flow is, we can then use Ohm's law again to find out what the voltage across, oops, that wasn't very clever of me. We can find out what the voltage across our intake air temp sensor is going to be, and that is the voltage that our ECU will find. Now, to make that a little bit clearer as well, I'm going to go through the process here of just showing you how that all works, how Ohm's law works. So we'll head across to my laptop screen here again, and in this case, the sensor that I just showed you from Motorsport Electronics has this nice calibration table here with all of the data that we're going to need. We've got our temperature, we've got our resistance, and we've got our voltage. However, in some instances, we are not going to know, in some instances, that data won't be presented with voltage as well. Instead, what we'll get is simply temperature and resistance. And in a lot of ECUs, we don't get the ability to directly enter resistance. Instead, the ECU is interested in the voltage that it's going to see. So we need to actually create that information ourselves. I am getting a little bit ahead of myself though. I just want to jump back a step. I'm going to show you in Excel how we can generate that voltage data, basically replicate that table. But first of all, let's just actually have a look at the options that are available for getting one of these air temp sensors or analog temperature sensors into an ECU. So we'll head into our tuning software here. And what we're going to do is have a look at our options for inputs. So when it comes to inputs, we've got the ability to have analog inputs. So we'll open up our analog inputs. And with our analog inputs, we've got 4, in this case, analog temperature sensor inputs, and then we've got a range of analog voltage inputs. In this case, we've got 12 analog voltage inputs. Now, the thing that differentiates between an analog temperature input and an analog voltage input, and this goes for the majority of ECUs, is that the analog temperature sensor inputs, unsurprisingly, as their name would suggest, is designed for directly connecting up to one of these negative temperature coefficient thermistors. So what it does for that very reason is it has a built-in pull-up resistor inside of the ECU. So that 1K pull-up resistor that we just looked at the circuit for, that will be housed inside of the ECU. On the other hand, the analog voltage inputs are more usually used for a sensor that already outputs a variable voltage, maybe a map sensor, maybe a throttle position sensor, any sensor essentially that will give a 0 to 5 volt signal. So for that sort of sensor, a pull-up resistor is not necessary. That's all done by the sensor. You give the sensor 5 volts, you give the sensor a 0 volt reference, and depending on the conditions that the sensor is exposed to, it will output directly a variable voltage to the ECU. So let's have a look here at our AN Temp 1 input, and we'll have a look at our options there. So we can see that at the moment that is selected to be off. We're going to set that up, and for the moment let's call that our gearbox oil temperature. We can choose that from our drop down menu. So let's choose that option, and this will give us all of the other options will now become available. So we can set an error voltage level. So this is just some diagnostics. If the circuit is open circuit or closed or straight to ground, it will trigger a high voltage or a low voltage warning. And in both of those situations, we can also select what the default value will go to, in this case 150C. This is the important part for us though. We can see that we have a pull-up resistor. In this case, 1 kilo ohm internal is selected. We can double click on that, and we've got a range of options here. We've got either a 1K or a 10K internal, or alternatively you can add your own external pull-up resistor, and in this case the ECU will disable the internal pull-up resistor, and it will do the calculations so that it knows what voltage to expect from the particular sensor. In this case, again, while we don't have to have a specific resistor, I'm going to leave that at 1 kilo ohm, and we can then go to our sensor type. So for the majority of the common sensors, there will already be a predefined sensor available. However, we're going to just have a look here at using a user-defined sensor. So this is where we'd have a data sheet like that one we just looked at and set this up ourselves using a cal table. So once we've done that, obviously we then need to input some data into the cal table. So let's have a quick look at that. So we'll go to cal table 1, which is what we were using. Now, I do apologize because with these changes that I've made, it comes up in red, so it's a little hard for you to read, but the input units, and a nice feature with the Link ECU, we can either choose to set this up in ohms or volts, and that's not always going to be the case, but either way, basically, as long as you've got the data, you're going to be able to calculate, as I'll show you shortly, what that's going to come out to be. Then we can choose what the units are for temperature, as well as the start point in the table and our increments. And then if we double click on our cal1 table, we can then set that up. So remembering again, this is voltage. I've actually got numbers in here that clearly represent resistance. Hopefully we're not going to have 65,000 volts going into our ECU, but once we've got that table filled in with the data from our data sheet, we're going to have a sensor that works. Okay, so for most tuners, that's about as far as things go. They don't really need to think too much harder about pull-up resistors. However, you can get yourself into a situation where you've run out of analog temperature inputs on the ECU header plug, but you still want to add more temperature sensors into the ECU. And this now represents a problem, and this is a situation where you do need to know about pull-up resistors. And the reason for this is we can actually repurpose an analog voltage input for the purposes of adding a temperature sensor, but in order to do so, we're going to need to wire in an external pull-up resistor to 5 volts at the ECU header plug. So let's have a quick look at how we would do that. We'll head to our analog voltage settings this time. Just load that up, and we've got, in this case, let's look at our analog voltage input 10, and we'll turn that on. So we've got all of the usual sensors that you would normally see with a analog voltage sensor, map sensor, MAF, throttle position, etc. But if we cycle down, we can see we've got the option to add some temp sensors here. So engine coolant temperature, air temperature, general purpose temperature, and each of these is denoted with external pull-up. So that's just a little reminder that you're actually going to have to do some work here yourself. So let's set up a general purpose temp sensor. We can give this a label so that we know what that's going to be. Let's call this diff temp. That'll probably be fine. And then we've got exactly the same situation here. We've got our calibration that we're going to be using, in this case, cal table 1. In this case, because it is an analog voltage input, we are going to be doing that calibration in terms of voltage. And then we've got our high error, our low error, and our error value. So once you've got that set up, you can then set up your calibration in the ECU, and that temperature sensor will read just as well as if it was going in through an analog temperature input. Now that I've filled in the blanks there, we're going to go back to where I was, and we'll look at how we can generate the voltage data. So let's just head back across to our spec sheet here. So this column here is what we are going to be trying to create. Now, remembering again that this just works on Ohm's law, we're going to be calculating the current flow through the circuit, and then we're going to be using that current flow, multiplying that by our variable resistance from our temperature sensor to work out the voltage that the ECU will be seeing. And just again, we'll have a quick look and show you what that actually looks like. So we've got our 5 volt source basically here, going through our pull-up resistor, which is here. Then we've got our temperature sensor in the circuit, and then finally that is connected to ground. So what we really want to do is basically calculate the voltage in this part of the circuit here, which is what the ECU header plug, the analog voltage input, is connected to. So let's head across to my Excel spreadsheet that I've got set up here. And what I've done is I've just entered the temperature and the resistance values straight from that data sheet that we've already looked at. And I've also put in a pull-up resistance here. The nice thing about setting this up here is that if you do it like this, you can then choose to change your pull-up resistor value. Not too sure that'll often be handy, but you can choose to do that and it will change the voltage calculation for you. So let's see if I can get this right. So what we want to do is start by hitting equals, and then we're going to have 5 volts. So that's our voltage, and then we're going to divide that by our total resistance. So we've got the divide sign. We're going to do our open brackets, and then what we want to do is add the 2 resistances. So for this point, it's our 72,300 or 72 kilo ohms, and then we're going to add that to our pull-up resistor value. Then we can close our brackets, and then that is going to calculate there the current through that circuit at minus 20 degrees centigrade. What we're then going to do is multiply that out just by our resistance at that temperature. This is our voltage divider. Remember, we're trying to find that voltage that the ECU is going to see. If we press enter, you can see that gives us 4.932 volts. Now, what we're going to do is drag that formula down to fill in the rest of the table. Before we do that, I'm just going to make a little modification here. Using the $ symbol here, we can fix the cell for our pull-up resistor so that that's not going to go haywire. What we'll then do is highlight the cell with the formula that we want to drag that down, and it'll fill in the rest of the values. So if we now check, let's just take one value here. Obviously, at minus 20 degrees C, 4.932 volts. We'll head across to our data sheet, 4.932 volts. Now, this might seem all superfluous, unnecessary. Who cares? You've got that data sheet. But I always believe, regardless whether it comes to wiring, engine building, or tuning, that having a basic understanding of what's actually going on behind the values there is going to be really helpful, and particularly if you get yourself into a situation where you've got a data sheet that doesn't have those voltage values. It's really easy, as you've just seen, to use an Excel spreadsheet or Google Sheets to calculate those values. And the nice thing about doing this here, as I mentioned, once we've got that all set up, if we wanted to maybe change our pull-up resistor to 10,000, we can do that, and the voltages will automatically adjust. So really easy to go ahead and do that. All right, we're going to move into questions and answers really shortly, but just before I do that, I just wanted to show you another couple of bits inside the Link ECU where this pull-up resistor comes into play. So obviously we've looked at our temperature inputs here. What we'll also do, excuse me, is we'll just have a quick look at the setup for a digital input. So for example here, we've got our aircon request on our digital input 1. So we'll head across and have a look at that. So this really comes down to how the sensor switches, or how the input switches. In this case, you can see that we've got our pull-up resistor switched to off. And the reason for this will be that when the aircon request is going into the ECU, rather than the aircon request from the factory car switching to 0 volts or to ground, what it'll actually be doing will be switching to a high voltage. So in that case, you do need to be careful with your pull-up resistor, because if you turn the pull-up resistor on here, when the aircon request isn't present, we're going to be seeing 5 volts because of the pull-up resistor. And of course, when the aircon request switches on, we're staying at a high voltage. So again, the ECU sees no determination between the switched on and switched off position. So with a digital input, we're going to need to use the pull-up resistor if we're switching to ground. If we're switching to a high voltage, then we do not want to use our pull-up resistor. In this instance as well, we can also select what voltage level the input will be considered to be on in. The other thing that is important to understand here, let's just head back across to our analog temperature inputs for a second, is when it comes to our pull-up resistors, and the fact that with the analog temperature inputs on the link ECU, these are software selectable, so we've got the ability to turn our pull-up resistors off. The reason we may want to do this, and this would probably be quite rare, would be the situation where you are installing an aftermarket ECU in a piggyback application where you're piggybacking the factory ECU and you want to share the input signals from the likes of the intake air temperature and the engine coolant temperature. Now, in that instance, the factory ECU, for exactly the same reason, will have internal pull-up resistors on those analog temperature input channels. So if you connect up an ECU and you share that signal, and the aftermarket ECU you've just piggybacked in also has a pull-up resistor, this is going to play havoc with the values, basically turning them into nonsense. So if you are piggybacking a factory ECU, you can still do that as long as you turn the pull-up resistor off. Unfortunately, a lot of aftermarket ECUs don't have software selectable pull-ups on their analog temperature inputs. They are permanently hardwired in there, so doesn't give you a lot of option unless you want to maybe set up the temperature sensors through an analog voltage input, or alternatively you're going to be stuck with adding your own external sensors. Alright, that has got us to the end of our webinar. Obviously a pretty simple topic really there. There's not a lot to understand, but I just know that there are a few key areas that people still get tripped up on, and particularly that little demonstration there showing you how to convert between resistance and voltage, provided you know the pull-up resistor value. That in its own right is really powerful to keep in the back of your mind. That was just a taste of what we put on every week for our HPA Gold members. Our Gold members are able to watch these live and ask questions and get answers while we're presenting. After the webinars have been hosted live, they're added into our webinar archive where our Gold members can re-watch them at their leisure. We've currently got over 240 hours of existing webinar content covering topics on engine building, engine tuning and wiring. This is one of the fastest ways to expand your knowledge on a wide range of topics, as well as to stay up to date with the latest tools, trends and techniques in the performance industry. Our Gold members also get access to our private members-only forum, which is the best place to get fast answers to your specific questions. Gold membership can be purchased for just $19 per month. However, you'll also receive 3 months of free access with the purchase of any of our courses. Click the link in the description to learn more.